Modern AI is, let's face it, astonishingly powerful. But behind the scenes, there's this massive problem brewing. These incredible models are also incredibly memory hungry. And that's creating some serious performance bottlenecks.
Which brings us to the big question for today. How on earth do you make an AI model 6 times smaller and have absolutely zero drop in performance? I mean, it sounds like it should be impossible, right? Well, a new set of algorithms has just done exactly that.
All right, to get this, we got to peek under the hood at how an AI actually thinks. It uses something called high-dimensional vectors. The best way to imagine these as a super detailed digital fingerprints for any concept. They capture everything about the meaning of a word or the features in an image across hundreds, sometimes thousands of different dimensions. They're incredibly powerful, but their very complexity is what's eating up all that memory.
And this is where you get a massive traffic jam. It happens in a really critical part of the AI's brain, called the key value cache. Now, this cache is supposed to be a high-speed digital cheat sheet for the model. But when these huge, clunky vectors all try to cram their way in, it just gets completely clogged, and everything grinds to a halt.
Okay, so people have tried to fix this before. The go-to solution was a technique called vector quantization, which is really just a fancy way of saying data compression. But as the research shows, the old ways had this fatal flaw. They brought their own memory overhead to the party. It's like trying to pack a suitcase more efficiently, but to do it, you have to add a bunch of heavy, empty boxes inside. It kind of defeats the whole purpose, right?
But this is where things get really interesting. Meet the solution, TurboQuant. This is an algorithm that pulls off extreme compression without that costly overhead, and this is the most important part, with absolutely zero loss in accuracy.
So how does it pull off this magic trick? It's actually this really clever two-step dance. First, it does this incredibly high-quality compression using a method called PolarQuant. Then, step 2, it uses a second algorithm called QJL to basically hunt down and zap any tiny errors that are left over. Let's dig into both of these secrets.
All right, let's pull back the curtain on secret number 1. It's all about taking a totally new angle. This is how PolarQuant completely beats that memory overhead problem we were just talking about.
And this slide just lays it out perfectly. You know, normally we describe a location with coordinates like go 3 blocks east, then 4 blocks north. Simple enough? Well, PolarQuant flips that script. It says, nope, just go 5 blocks total, but at a 37-degree angle. You end up in the exact same spot, but the way you describe getting there is fundamentally different and way smarter. And here's why that is so brilliant. By thinking in terms of a distance and an angle, the data gets mapped onto this nice, fixed, predictable circular grid. The old methods were stuck with a messy square grid, where the boundaries were always changing, which meant they had to store all this extra info just to keep track of it. PolarQuant just gets rid of that problem entirely. That memory overhead, gone.
Okay, but that's only part 1 of the magic. Now for secret number 2, the 1-bit trick. This is where that QJL algorithm steps in to act as this perfect mathematical error checker.
Now get ready for this, because QGL is just wild. It's a mathematical technique that takes complex vector numbers and crushes each one down to a single sign bit. We're talking just a +1 or a -1. And the craziest part? It costs 0 extra memory to do it. Nothing.
So you're probably thinking, how on earth can it still be accurate if everything's just a +1 or a -1? Well, that's the magic. It's all about balance. When the AI needs to make a decision, QJL strategically compares the original high-precision request with its super-compressed 1-bit data. And through this balancing act, it calculates a final score that is just as accurate as if it had used the full uncompressed vector. It's pretty incredible.
So you've got this clever new angle with PolarQuant and a wild 1-bit error-checking trick with QJL. It sounds amazing on paper, right? But does it actually work? Well, let's look at the results when they put TurboQuant to the test.
First, the headline number, a 6-fold memory reduction. That's not a typo, a 6 times reduction. And this is the kicker. This was achieved with perfect results on what are called needle-in-a-haystack tests. These are brutal tests designed specifically to see if a model loses its ability to find tiny, specific details in a massive sea of text. It didn't lose a thing.
And we see this play out across the standard benchmarks too. This chart shows performance for the popular Llama 3.1 model. That Kiwi baseline at the bottom, that's the old way. PolarQuant on its own is already a huge improvement.
But then look at TurboQuant. It consistently scores the highest. It's on another level.
And it's not just about size, it's also about speed. And this part is just mind-blowing. When they measured it on powerful H100 GPUs, 4-bit TurboQuant was up to 8 times faster at computing the core logic of the model, compared to the original, uncompressed version. So it's smaller and way faster.
This has huge implications for things like vector search. Here, we see TurboQuant going head-to-head against other state-of-the-art methods. It achieves the best recall, which just means it's the best at finding the correct result. But what's even more impressive is that the other methods had to be specially tweaked and tuned for this specific dataset to get their results. TurboQuant? It just works right out of the box.
So, okay, let's zoom out. We've seen the tech, we've seen the numbers. What does this all mean for the bigger picture? Why does this change the game for AI? Well, we're moving from a world of bottlenecks to a world of new breakthroughs.
And the real-world impact is immediate. This directly solves that KV cache bottleneck in massive models like Gemini. It makes semantic search, the kind of search that actually understands meaning, faster and more efficient, even at Google's scale. It lets us build powerful AI that operates with incredible 3-bit efficiency while maintaining the precision of models that are way heavier.
And maybe the most important takeaway here is that this isn't just some clever engineering hack. The researchers make it crystal clear that these methods are backed by strong theoretical proofs. They are provably efficient and operate near the absolute theoretical limits of what's even possible. And that makes them robust and trustworthy for the critical systems that are going to power our future.
So we'll end on this thought. For the longest time, there's been this brutal trade-off in AI between power and efficiency. TurboQuant shows us that we can actually have both. So the question we're left with is this. Now that AI can be both powerful and efficient, what new frontiers is it about to conquer?